So it's a great honor to be here. My name is Garrett Smith. I'm from Chicago. And I've been coming to Krakow here for about 3 years, and I have seen some pretty amazing things going on in this city. I was here earlier this year at Lambda Days, and there's something going on in the tech community here. There's a community here of programmers who are investing time. Is it possible to turn this down a little bit? Maybe half? It's very loud up here. So if you're privileged as a programmer to live here, it's a pretty exciting time, I think. I mean, there's user groups popping up all over the place, amazing conferences. This is an amazing conference. I would encourage you, if you live here, to invest in the community. Spend some time, go to user groups, go to conferences. If you are interested in something and there's no user group, go create one. I will tell you there's something special here, though. I've been to a lot of cities in Europe, and the energy level within Krakow, especially in the developer and the startup community, is pretty exciting. And I'm really happy to be here. It's an honor. So, name is Garrett Smith. I'm not famous. I haven't written any books. I haven't written any software that you probably have heard of or use, unless you are an Erlang programmer. I don't have any groupies. I did write this video, made this video a few years ago. MongoDB is web scale. And if you haven't seen it, it's a video with two bears and they talk for 5 minutes in a computer voices. So you would think that's kind of lame, but the video does say some things that people think is funny, and it went viral and great. But it wasn't until a couple years ago that I was sitting in a bar overhearing a conversation. Somebody made a joke about something being web scale. Blah, blah, blah is web scale. And then somebody laughed about it. And I thought, oh my gosh, this is actually leaked into culture somehow. This is like a random event that I was a part of. They didn't know I was there. It wasn't for my sake. Like, wow, that seems to have fulfilled my existence in life. That was really quite an experience for me. I'm exaggerating a little bit, but really, I am really interested in making people laugh about the insanity of our business. And so if you're here thinking I'm going to go through some architectural diagrams, Java Enterprise, UML diagrams, so anything like that, you're in the wrong place. This is going to be about tearing things down. This is going to be about making fun. But I think when you make fun of something, it's satire, right? If it's constructive, it actually has a benefit. You laugh because it's true. So I hope to be poking fun at things that are true in a constructive way. But make no mistake, this is going to be one of those talks. Okay. So let me begin the story here with this question. Do you ever see this? Will it scale? Do you ever see this in a mailing list? If I'm using this thing, how can I make this scale? Have you ever talked about this topic when you are collaborating with your colleagues? But will it scale? Will that design decision scale? Well, I hear this thing all the time, and it amazes me how many people swarm around the topic to answer specifically. So somebody's like, well, how do I make this thing scale? Oh, well, I know how to do that. You use this database, this key value store, and this pattern, right? And then this thing over here, and it'll totally scale. I'm like, how can you possibly be so specific? The question was very general. Doesn't really mean anything. Will it scale? What do you even mean by that? Yet people are incredibly specific. I, on the other hand, tend to reject specific solutioning here. I tend to reject the question. Here's how I would answer this question every single time. And this is a pattern that's developed, so I'm just sort of reflecting on the pattern. So here's my approach to this problem. First of all, when it comes to something to scale, does it exist? Have you created it? No. So you're interested in scaling something that doesn't exist. How about this? Let's make it exist first. Right? If we're talking about an Olympic athlete, how about making it born? Right? How about something to start with? That's step number one. Step number two is after you built something, put it in production, deploy it. Software that doesn't run into production is much like a tree that falls in the forest and no one is there to hear it. It doesn't make any sound. It's a philosophical thing. Software that doesn't run is really not that interesting. So deploy it. Third step, observe it. So put it into production, watch it, observe it, take note of its performance characteristics. Now, you'll see things that work well, you'll see things that don't work well. Fix the things that don't work well. That's the answer. But this approach is not satisfying to people. People will answer this way. This is the response. So my response, and then their response to me is this. Thanks, Garrett. Thanks a lot. Thanks. You just kind of blew me off. I asked specifically about scalability and you told me nothing about scalability. In fact, you kind of made fun of me, and I feel bad. So we get at odds here. But the thing is, I wasn't making fun of them. I was being genuine. I was being serious. This is actually what I think is the right response here. You know, you build it, you deploy it, you observe it, you fix it. So this is this disconnect. Confused me. Then I realized something, that the question that they're asking here seemed to be technical. It invited a series of technical responses. But actually, it wasn't. It was emotional. What the question, will it scale, or I want to build something that scales, is actually a statement of saying, I want to build something great. I want to be like Google or Amazon or Yahoo or any of these great companies. I read these blog posts, and I become a little envious about all the awesome things that they're doing, the amazing things in software that they're doing, so I want to do that. That makes sense. So here's my proposal. Now, you may think that I'm joking. I'm dead serious. I want to actually propose something. We change the word. I want to change the word scalable to awesome. Dead set serious. Awesome has as much semantic meaning as scalable, but it's more fun to say. Check this out. Okay? Bear with me. You're skeptical, I can see that, but give me some time and I will hopefully prove to you that this is the right decision. And then we can start a movement here, Traco, and they can say one day, when the word scalable is eradicated, and you go to Urban Dictionary and you see under awesome, you see like the second meaning of awesome is something that is felt good in software that feels good and is great. Awesome. That will be a great accomplishment. Okay, let's try this out for size. Now this is a quote from a mailing list, and there's lots of them. Whatever mailing list you're a part of, if you search scalable, you'll see things like this. What is in the implementation of Erlang that makes it scalable? Oh, well, that's an interesting question. And everyone floods in to respond. How about this? Let's change this. What in the implementation of Erlang that makes it awesome? Now that thing I can answer. I can go crazy with this. We all can. We can get excited. We can talk about all of the amazing things in it. Right? Okay, so that's example number one. This is number two. I wrote a scalable Erlang system for my client. The system can handle hundreds of thousands of clients on EC2 and uses up to 200 instances. Wow, I have no idea what that means. But let's change it. What does it mean if I wrote an awesome Erlang system for my client, et cetera, et cetera? Doesn't this seem more fun? This is more liberating. We can talk specifically about how cool the software is. Finally, my last example. Building a massively scalable web server in Erlang. This was a tutorial that some bozo proposed at OSCON last year. He actually ran a 3-hour tutorial on building a massively scalable web server. Of course, that bozo was me. I ran the tutorial. It was a joke. It was funny. I mean, come on, 3 hours, you're going to build a massively scalable web server in Erlang? This is what I should have said. This is more fun. Building a massively awesome web server in Erlang. Now, that's actually what we did. We took 3 hours. We had a lot of fun. We saw things scale. Actually, what that means is they performed a certain way, and we observed that. And we observed when it started to fall over. We got into some, but it was awesome nonetheless. The benefit is simply this. Same semantic meaning, more fun. Now, I know you think that I'm just sort of poking fun here. Bear with me. You will see some specifics. I will spend the rest of this presentation talking about 3 things. The myth of scalability. This is why we should not use the word. So I'm going to make that point. 2, our obsession of scalability. I think that there's something going on here. I think that physiologically, as a community of human beings doing programming, something kind of weird is going on, and I think I understand what it is. So I want to talk a little bit about that. So those are kind of my tearing down stage. Finally, I want to talk about some scalable, awesome patterns that we can actually apply. And this is content that you can actually apply. And it has nothing to do with scalability per se, but it's awesome nonetheless. Okay? All right. So when you talk about the myth of scalability, I think there's one thing that you want to take a look at, and it's very simple. It's an outage. When something doesn't scale, it manifests as an outage of some type. And an outage can be lights out, not working, or it can be not working the way it should. That's an outage. Every single large company that has gotten large has gone through outages. Not one, not two, dozens. Many very popular and well documented. Remember Twitter? When was the last time you saw the fail whale? Do you remember the fail whale? Remember that? You go to Twitter and the site is down. This was before they figured some things out and started to chip away at the problems that they had. But the great Twitter, which, the statistics are astounding what they are doing today, experienced massive recurring outages. So no, I guess they didn't scale. But they're a scalable company. So what's going on here? Failure and success. Does it make any sense to talk about Twitter as not scaling? All right. How many people use the web services by Amazon? I do. I'm a fan. I love it. They're great. I also hate it. I had 3 consecutive all-nighters due to outages related to Amazon, AWS. So I have some bitter feelings about that. But this is Amazon. This is the great Amazon. If there's anything that scales infinitely, it's Amazon, except that they experience outages. Not as many of these days, but in the early days, quite a few, quite regularly. They went through growing pains. So this idea of scalability, where is it? Where does it exist? What is it specifically? Of course, there's well-documented scalability issues of eBay, and frankly, anybody. Anybody. The problem with the word scalability is it doesn't mean anything. It's like magic. It's like saying, I want an infinitely dialable dial in the cloud. I don't want it to go to 11. I want it to go to infinity. Just keep spinning it and spinning it and spinning it. There's no such thing. The bottom line, and you can read all about these things, many of them are generously documented so that we can learn post-mortem style why things fell over. And when you read these things and read these post-mortems, you start to see a pattern. It's not, we need a scalable architecture, we need to make it scale. It's the process that I described earlier, the 4 points. Build it, deploy it, observe it, fix it. It's process-oriented. And you'll see the mode to recovery is about implementing those 4 steps. It's not about deploying some magic, some formula that once we put it into motion, we can step back and say, our system scales. That doesn't exist. The bottom line is nothing scales. There will always be something that can put your application or your system flat on its face. Generally, we don't run into those things, but when we do, what happens? Application falls on its face. And the permutations, the possibilities are probably infinite or near infinite. Right? To identify what makes an application fall over is not a discussion of scale, it's a question of physics. What's going on? What is affecting the latency of the communication from this node to this? What are we doing here that's causing our performance to go up, our latency to go up by 100? Well, probably you're hitting disk, or 1,000 in the case of a disk. There's specific things, and they occur in time and space. It's physics. So when we use the word scale, what we're doing is we're stepping back from physics. Because at any point, there is something that you can identify, and that, as engineers, is what we need to do. Scalability is a shit word, and we shouldn't use it anymore. What should we use? Okay, I hear some fans. I hear some converts here. Still some skeptics. Okay, it's okay. I still have some time left here. That's right. We want to use the word awesome. This is really talking about what we mean. We're not interested in solving actual engineering problems. We're getting excited, and that's fine. Let's get excited. Let's get pumped up. High five. We're here to build amazing, beautiful, incredible software. It's exciting, so let's get excited and let's embrace that. So I'm going to propose a word here. Now I know, that's just kind of ha-ha fun. What do you do after you've celebrated and sort of self-aware, I'm building something awesome? What do you do? Well, let me propose a word here. The word is sexy, so be careful. Here it is. Over time, I have become more and more attracted to this term suitable. So by suitable, I just mean it works. It does what it needs to. No more, no less. It is suitable for the task. Sufficient. The reason I like this word is that it shows up in nature. When you look at natural selection and the invention, the invention engine that is natural selection, you see not survival of the fittest or the most advanced or the most awesome. You see simply survival. Survival is survival. It is what is needed to survive, to exist. The things that don't exist are removed. The things that remain are suitable. Let's take a look at our favorite land animal, the cheetah, fastest land animal. The physiology of the cheetah is pushing physics. So it's difficult to make this animal go any faster. A human being on a bicycle, the fastest human being on a bicycle is roughly equivalent in speed to the cheetah. And that's after all of our engineering effort in a bicycle and the mechanics, the advantage there. The cheetah had none of that. The cheetah simply is awesome by itself. But it's not because the cheetah sought awesomeness. The cheetah did not seek. The cheetah knows it's awesome. The cheetah is fast, very simple, because its food is fast. The cheetah doesn't get up in the morning and say, I want to be the fastest land animal. It says, I could go for antelope. I'm hungry. And in order to eat, in order to exist, the cheetah goes fast. It's simple as that. So as a point of contrast, let's consider a slow food source. That's a blackberry, not the phone. It's an actual fruit. Now this prey is very, very slow, and it is the victim of this vicious predator. The turtle, not very fast. But when you compare the relative speed of predator to prey, he is literally infinitely faster than the cheetah. It's true. So this is suitable. The turtle doesn't have to go super fast because its prey is not fast. It's a vegetarian. However, it is slow and is subject to predation by faster animals. So what does it have? What does the turtle have? What's its secret weapon? Not X-ray vision. Don't say that. What's its secret weapon? The shell. Excellent. This is its secret weapon. This is a true story. This actually happened. This isn't photoshopped. It's not a Disney cartoon. An alligator did battle with a turtle here for 15 minutes, and this shell held. And held so much that apparently this turtle is enjoying the ride. I mean, I would, if I was a turtle, be like retracted in the shell, but this guy's badass, and he's just like, hey man, I can take this as long as you can. This is actually pretty fun. So nature has given this animal what it needs. So we have fast and we have slow, but it's relative. What does it even mean? What does fast mean? Joe Armstrong, the creator of Erlang, says, there's no such thing as fast. There is no such thing as fast. There's no such thing as fast, only fast enough. That's a suitability standard. If we can simply absorb this concept and get the hell rid of the scalability topic and just talk about what we need to do, we're well on our way to solving actual engineering problems and building actually awesome software. Not a sexy term. It's going to take some time to get used to. But suitability is a very, very powerful mental model when you're building actually awesome software. So I want to talk a little bit about this fixation. I really think we're fixated on. I mean, when was the last time you read a blog post on suitability, on doing just what you need to? We don't care about that. We're interested in going as fast as we possibly can, more volume, faster, bigger, stronger, and I believe it's this. It's this phenomenon. We have sporting events that select out of our population the very, very strongest, the very, very fastest. And the whole world, except for those of us who program and don't care about this stuff that much, watch these events every 4 years. And we marvel at all the records that are broken, and we keep track of them meticulously. We are consumed with optimization. Who is the best? Who is the fastest? Nature is not, but somehow we are as human beings. So where does this come from? Where does, for example, the shot put come from? You know the shot put, that event where you basically throw a rock as far as you can? Where did that come from? Joe's like, hey, watch how far I can throw this rock. He throws the rock, boom, we have the Olympics. Where does this come from? The javelin, how far can I throw a spear? Doesn't take much creativity to imagine where this came from. We have a long-standing history of being programmed for survival, for competition amongst ourselves, and to get prey, to avoid prey. We've been programmed to go fast and be strong. This is in our programming. We can't get rid of it. So it makes sense that when it comes to software, we are consumed with something just arbitrarily faster. Hey, Joe, look how far I can throw this database, right? Hey, and there's a competition. Do we need to do that? Do our users care about that? Does it make our applications any better at all? Oh, doesn't matter. It's awesome. It's an emotional drive to build great things, which is fine, but it becomes very difficult to address specific engineering problems when you're off in the world of arbitrary performance, this fixation on optimization. Okay. I actually think this is a very serious problem. And I'll tell you why. How much time do we spend doing things that we don't need to do? Like what percentage of the time? 10%? No way, man. It's a lot more than that. I believe that if we were to allow pure necessity to drive everything we do, we could probably easily cut our workloads in half. Just doing what we had to do. Suitability standard, not optimization, not scalability, not even awesome. Right? Simply, what do we need to do? Half of our time. Imagine what you could do with another set of time. Double your time with the availability. That costs money. It delays things going to market. It irritates customers. You build the wrong thing. You optimize in the wrong area. It's fundamental to the things that we do in software. So I think this topic is extremely important. The psychology around building something that is awesome and its dominating force in our industry has kind of hurt us. So I'd like to call attention to it. Okay, that's the destructive part. What I'd like to do right now is propose some patterns that are awesome that really have almost nothing to do whatsoever with scalability. But you can apply them, and I think they're valuable. This is sort of a distillation of patterns that I believe are, for me, probably the most important thing. I was trying to add some things, and I thought this is the minimal set. So from my point of view, this is really good information. But it's like my original answer to the question. It has nothing to do with going fast or building super awesome, incredibly scalable software. So you'll see. Okay, so I'm going to name these patterns, and then I'm going to go into each one of them. These are named kind of shortly and catchy. So one is called not a problem, build it naive, dependencies bad, think system, and physics not magic. So these are patterns. You can say, I'm going to pull out the build it naive card, think system. So you can think of these just as simple labels applied to a more complex pattern that you can apply to things when you are building awesome software. So let's take each one at a time here, not a problem. So, do you know that there is one solution at least to every problem? This is true. There's at least one solution to every problem, and that is to deem it not a problem. Problem solved. And I do this, and I get a similar reaction. I get chuckles. And I'm like, I'm actually being serious here. This is not a problem. We don't need to solve it. Problem solved. It's very important, I believe, to scrutinize every single problem presented yourself. It could be a problem that popped into your head, or it could be a problem that was handed to you with, triplicate and stamped with the great authority from above. Here's my problem. Every one of us should challenge this as a problem and consider, is this something that we need to solve? Is this something that we need to solve right now? I don't know why it does that. There we go. Okay. There are problems that we may have to solve in the future, and then there are problems that we must solve right now. And I believe every problem goes through a filtration system, and we should consider this as a pattern before all others. So it's the one that you consider, is this a problem? And you can say, not a problem. There are so many things. And I come from a Java background. I understand how much speculation goes into design in a typical Java program, in a class hierarchy, in an architecture. I understand that. Ask yourself every time, what problem are we solving here? I think in a lot of cases, the question is really, how many new problems have we just created by doing this, by taking this approach? So I would encourage everybody to consider this wonderful solution to a problem when it makes itself available. Now, when you have actual problems that you have to solve right now, introduce the next pattern. Build it naive. What do I mean by this? So I like to call this the unclever approach. I used to call this stupid, but stupid is a bad word. You don't want to use the word stupid, so unclever. No one wants to be clever. If you call yourself clever, don't do that anymore. You want to be unclever. You want to be basic. You want to be grounded. So the unclever approach looks like this. We take obvious line-of-sight solutions to problems. So it has to be obvious. It has to be visible. We don't speculate and look down at the horizon at what might be. That is clever. That is forecasting. That is some sort of prognostication. You're being clever there. Be unclever. Take the naive approach. Obvious line-of-sight solutions. The benefit of this is because it's obvious and because it's line of sight, it usually works. Usually does. If it doesn't usually work, it probably wasn't obvious and it probably wasn't right in front of you. Things that are obvious and right in front of you tend to work. That's a good thing. Working is good. It's shocking how often these things will work forever. So I encourage you to try it. Just try it. Try it. What could go wrong? Just try it in an experiment and see how long your stupid or unclever, obvious line of sight solution lasts. You will be surprised to find that many of these last forever and you never have to touch them. The benefit, obviously, is that it's cheap. You're not investing in speculation here. You're going right for the throat. This is what we need to do. And here's the hidden benefit. It will get you closer to the actual problem that you have to solve. And you see this in Agile quite a bit. But I believe that you can push this all the way down into the low levels of software construction. The things that you build, the design decisions, how you architect, how you make decisions about A, B, or C. The real teacher for problems is experience. Again, build it, deploy it, observe it, fix it. You have to get real-life experience with something. And taking the naive approach where you build something in an obvious line-of-sight way gets you down the road to the actually interesting problems. And I'm talking about the physics here. I'm not talking about agile methodologies. So that's the build it naive pattern. The next pattern, dependencies bad. How many people here love dependencies? You love dependencies. I love dependencies. I hate them passionately, and every year that goes by, I hate them more and more and more. Why? Because every dependency that hurts me, I remember it. It wounds me, and it makes me a more fragile individual, and it makes me an angrier individual, and I remember all of them. And so every time I see a dependency and something comes up and bites me again, it's in the back of my mind. And now I'm like a rampage. Every dependency I fight against. And someone said, a friend of mine, she's like, Garrett, what's your issue with dependencies? Why are you so angry with dependencies? Well, obviously hurt you. They do hurt you. And I'll show you an example in a moment. The problem with dependencies is that dependencies come with dependencies. You say, oh, I want to introduce this library. I want to introduce this database. I want to introduce this subsystem. Along with that comes all of its dependencies. So that's a big tree. And it's often very difficult to understand what it is you're buying into. Because dependencies are something that you depend on, and they can hurt you. So let's take an example of this. One day, I worked for CloudBees, and we used to run a platform as a service. So as a Java developer, you would program your application and then push it up to our platform. And we would run it and host it, monitor it, scale it, etc. Oops, I did it. I made a mistake right there in real time. We don't scale it. What do? We make it awesome. That's really what we did. We made it awesome. So one day, all sorts of hell broke loose with user message or trouble tickets. We just were flooded. Not a single application was being deployed. Everything was failing. All deployments were failing, every one of them. And we looked at our systems and we said, everything is up, everything is green, everything is working perfectly fine. What on earth could possibly be happening here? So we took a little bit of time and we investigated it, and we discovered that it was this XML file. That's a little bit difficult to read, but don't worry, it's XML. It's designed not to be readable. So as it turns out, innocuously, this is metadata, by the way, that each application uses. So you need this file in order to deploy the application. So without this metadata, we don't know what to do with your application. So the problem here was this. Schema location. Can anyone guess what was going on there? Why our entire platform had been brought to its knees? It still wasn't that obvious to us, and it was shocking what had happened. This, of course, is a reference to the schema definition for XML, so XSD. And what it was doing, we were using a validating parser, and the parser would go grab that XSD file. We didn't even know that was happening. So that was an additional latency that we weren't measuring. We had no idea was happening. And that day, this server, java.sun.com, was down all day. And all of our deployments were failing. Now, this is an example, one of thousands of examples of where a dependency on something can bite you hard. So in principle, just like in any good design, remove moving parts where you can. A reliable system is made up of fewer moving parts. All things held equal, more moving parts makes a less reliable system. It's a matter of statistics. It's fact. It's math. Fight against dependencies. So here's my mantra when it comes to dependencies. Number one, make do with what you have. So if you're just starting out and you don't have any computer programming language or no computers, I suggest that you get some. You need that to start. But, for example, many times a regular expression parser, which every system has, it's very easy to get, is perfectly suitable for a task. It doesn't have to be fast. It doesn't have to be elegant. You don't have to parse a DOM. You're not navigating a DOM. You just need to pull a pattern out of something. That's an example of millions of examples. So the first one is, can you solve the problem with what you have now? How hard is it? Is it difficult? Is it really that hard to go do this that we're proposing with what we have? Okay, well, maybe it is. Fine. Because the fact of the matter is, some dependencies simply overwhelm you. You need to use tools. You need to use libraries. But fight against it. Push it back and say, I don't want to use this until I'm overwhelmed by it. I must use this thing. So you fought. And then finally, as a matter of principle, when you are forced to give in, do so bitterly, hold a grudge. Really. I mean, I want this to sink in to the psychology. Dependencies are bad. We fight against them. They're a reality, but they are our problem. So we manage them. Okay, next pattern, think system. This is my favorite one. No, my favorite one is, I like them all. They're all favorite. But this one I like a lot. Think system. So what is a system? So I like to think of it as independencies, like it's sort of the opposite of dependencies. These are things that are independent. You design something to be comprised of components that are independent. And so we're talking about some sort of boundary. But more importantly, we're talking about a boundary in time and space. A lot of us as programmers are used to looking at boundaries in terms of code abstractions. So I'm not talking about code abstractions. For example, the boundary of some class hierarchy. That's not what I'm talking about here. That does not comprise a system. A system is boundaries in time and space at runtime. So if you're a system administrator running a bunch of independent processes and servers, you're used to system. If you're a Java programmer and aren't involved whatsoever in running the software, you probably are not as familiar with that. So there are some language cultures that embrace systems and others don't. This is not really a moral judgment. It is a little bit. It'd be nice to see languages supporting systems more explicitly. Libraries like Akka, for example, give you system view to things, but systems really need to be independent boundaries in runtime. So when I'm talking about boundaries, I mean like an operating system process, isolated heap. So you're not sharing heap. It's very difficult to build a system in a large global shared heap. You're relying exclusively on static checking in order to ensure the correctness and the correct working of that program. And when it comes to concurrency, it's very, 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 very difficult to ensure correctness. Type systems have a hard time with that. So what you do is you don't share heaps, you don't share memory. You push things off into their own boundaries. And the natural boundaries that occur in the stuff that we work with are operating system processes, virtual machines, all great hail Lord of Lords Docker, right? Containers, those are boundaries. You see where I'm coming from with some of these things. Obviously servers, data centers, these are natural boundaries. So when you lose something, it's independent, it's independencies. It's difficult to really put this into words, but I'm going to try. If you're building software today, you really are probably building a system. Maybe 20 years ago when we were doing client server, if it was probably more than that, we didn't really have systems. We had a sort of big monolithic application that would talk to a database. Yay, great. But as we're building for networked applications, our applications tend to sprawl. Maybe you're building an Android app, but you're also probably building an iOS app, and you're probably building a server backend. Maybe not you, but your team or your company. So you are participating in building systems. So think in terms of systems in the code that you build, and I would emphasize this language differentiation. Some languages are very good at this, and I will name a couple. I will name one that will surprise you. Bash is a very good systems programming language. It gets you into the bowels of the machine, not the bowels, I'm sorry, the operating system. You're scripting operating system tasks. You're creating cron jobs. You're gluing things together. You're very much thinking in terms of system orchestration when you use Bash. Now, if you're building an iOS app, don't use Bash. I don't think it would work very well. Maybe it would, I don't know. Erlang is a very, very good language for system orientation, simply because everything is done in Erlang using a process. It is a process-oriented programming language. It's impossible to build software in the language Erlang without building a system. In fact, they call it a system. When you start an Erlang VM, it's called booting a system. It's slightly esoteric, but you can think of it as an operating system for your code. If you're interested in functional programming, if you're interested in picking up another language, I would encourage you to look at Erlang. You will learn a lot of very, very useful things. You may not have a blast every second. Some things are challenging, some things are different, but you will learn a lot of things, system orientation being one of them. Okay, physics and not magic. And this is probably the closest thing that would come to actual scalability topics. And I don't really have enough time to get into all of physics, so I'm not going to. It's difficult to sort of give you a lesson on physics. I'm actually not a physicist. I don't think I could do it. But I can give you a taste. So, check this out. This is a list of relative latencies of different operations in computing. And if you haven't seen this list or lists like this, it's very, very instructive. Did you realize, for example, a level 1 cache reference is much faster than sending network I/O? I'm sure you did. I'm sure you did. That's probably obvious. But the orders of magnitude are very interesting here. So we have level 1 cache references. Skip a few main memory references. You can see, a couple orders of magnitude, 2 orders of magnitude, 3 there. Sending, reading and writing to a solid-state hard drive, all the way down to sort of the big expensive things, which is inter-data center network I/O, going over backbones. So when you're building something and having to address a particular problem, it's very useful to know where latencies are coming from. But again, this is going to be executed in the context of this other framework, which is build the thing, deploy the thing, observe the thing, that is, collect metrics, observe what's going on, and then make decisions about where you need to fix things. Now, you've got a problem. Oh, this is going too slow. Our users are irritated. Right? Or this is falling over at this level of concurrency. That's not a scalability problem. That's a specific problem related to your application in time and space, and you can measure it. And you can see we're running on this particular environment, this kind of hardware, this sort of network infrastructure. This is the software that we're using, and you can measure it all. And you can make informed decisions about how to improve things. Where does Scalable come into that? Awesome does. Scalable does not. They're the same thing, right? Awesome is more fun. So here's a fun idea. Again, given that I'm not a physicist and we don't have time to go through every possible scenario of how something could break. And when you go and look at the postmortems for a lot of these outages, these are very interesting reads. When it comes to topics of building awesome software, I would really encourage you to read the outage postmortems for anybody. You will always learn something very interesting. One thing that comes out is that there is no silver bullet. There is no thing that you do that makes something faster. It's a process. It's a process of measuring. It's a process of applying your experience, of course, of getting validation from other smart, experienced engineers when you tackle a problem. But it's an ongoing improvement process. There is no thing that you lay out that does it for you. You're constantly chipping away, constantly watching, constantly looking for things that might be falling over and addressing them, hopefully before they fall over. So when it comes to physics, this is a fun thing, and it's kind of tongue-in-cheek. I mean, I don't know how many Google engineers are doing this, but I would buy some of these if you don't have these. There's a class of devices these days that are very inexpensive. You know, you can buy them for 20, 30 US dollars, euros. It's roughly the same. Cool. These are cool. These get you into slower hardware. These are much, much slower than your laptop. Some of them are running on the same hardware that you'll have in your phone. Some of them are running on slower hardware than you'll have in your phone. When you write software for this, you can try running a big Tomcat application or JBoss application. Try it. It might work. But chances are it'll drive you into something else. It might drive you into using Python, or it might, Erlang works well on this, or C, or some other languages, and play around as a hobbyist. What I like about these devices is they're physical, they're real. They're not the cloud, they're not magic, they're not abstractions. And you have real hardware specifications that will get you into the space of physics. So when it comes time to tuning something, you'll just be more familiar with what operating systems are doing, what device drivers are doing, how something can work or not work in something that you're holding in your hand. And then what the heck, if you want to build really something awesome, just do something like that. Use Legos. Take a bunch of these things and build a cluster and do something truly awesome. I don't know where this goes. It's fun. And it gets you into the realm of physics. Well, what could go wrong here? It's a toy. And this is how we learn. This is how we have fun. It's an idea. Obviously, if you're running a system that is in production and you have real problems, you feel free to go and tackle those as well. Right, this is just a kind of a fun idea here. Okay, so I have some final thoughts. I don't know if we have a microphone here, so we can see if we have any questions. Well, I've got some time for questions here if there are any. Okay, so let's go through this again. What are we talking about? Is this what we want to use? If you think this word is useful, feel free to use it. I just made a case here. Maybe I wasn't persuasive. I'm going to try this. I'm going to try using that and just see how it feels. So far, so good. It's more fun, and it seems to mean the same thing to me, at least. So then I introduced a slightly more pragmatic and practical term of suitable. This is important. This is valuable. This is where we want to focus. Don't go building things that you don't need to build. Do what nature does, do what the cheetah does, do what the tortoise does, do what the blackberry does, the fruit. Build stuff that works, does the job, and that's it. And you can use these patterns, awesome patterns, and apply them, and I think those will help you. But I want to talk about one final word here which underlies the things that I'm talking about, and it's this word evolvable. When we build software, we are not building it discretely. We are in an ongoing process, and we need to be scientific about it. We need to get things into production and measure them. We have to. If we don't measure them, we have no idea what's going on. We can't rely on some framework that's going to be handed to us from Twitter or eBay or Google or whoever we think is awesome and lay it into our system and expect it's just going to be awesome. It's going to be super awesome. We can't expect that. We have to get into the habit of doing what we need to do, focus on what we need to focus, and measure that, and then get into the actual problems in time and space, the engineering problems, and address those. So what is that? What's going on there? That's an evolutionary process, right? What were the steps? Build it, deploy it, observe it, fix it, repeat. When you build software this way, you are involved in an evolutionary process. Your software, you will find, becomes more system-oriented. It becomes more direct, more ruthless, more pragmatic, more suitable for what you need to do. And as you run into problems, you solve those problems, the ones that you need to solve right now. You push off the problems that you don't actually have to solve. And yes, that's a debate. That's a detailed and very difficult conversation to have. But once you decide that something is a problem, then you solve it right there. And you push the stuff off that you don't need to solve. You'll find that you're building awesome software. I believe this. evolutionary process that is incremental. You start with something and you continuously improve it. You continuously modify it according to what you need, not according to what you want or what you feel you should be doing. We can talk about building awesome software all we want, but that's actually not going to build awesome software, because what we're going to do is build stuff that is arbitrarily fast. You know, a cheetah that has turbo boosters. And turbo boosters have absolutely no application to its existence. It's pointless, wasted time. We could have used that time to make something great, something our users care about. We're building these scalable scalable systems, which is, I think, largely an indulgence, so we can feel great about what we're doing. But if we're honest and focused and realistic and pragmatic, right, we will build, I think, great software, awesome software. So this is the last word I want to use, is evolvable. This, I think, underlies the entire story that I'm telling here. Okay, so I have a few minutes left, and I will use them. I don't know if this is working. Let's see, this is on mute. Problem solved. Are there any questions? I don't have any plants, so I actually need somebody to ask a real question. One person. Criticize. What don't you like about this? What sounds off to you? Do you buy it? Do you think this is interesting or useful? Nobody wants to say anything. That's okay. It's understandable. Here, come up on stage. It's great. It's very refreshing here. This is an amazing room. All right, well, I have said plenty about this topic, so I will end this presentation. Thank you very much. I appreciate your time, and enjoy the rest of your conference.